welcome, and thank you for attending our webinar on 4D STEM. I will shortly hand you over to my colleague, application scientist Matúš. Please ask any questions in the chat box. We will endeavour to answer these at the end. Our mission at Quantum Detectors is to provide the best detector technology as the fuel behind scientific discovery, not the barrier. Quantum Detectors was founded in 2007 as a spin-out from the UK synchrotron diamond light source and the Science and Technology Facilities Council. Our offices and factory are based on the Harwell campus south of Oxford. In 2012, our first commercial product, Express 3, came to market for synchrotron research. We have continued to develop our product lines for the X-ray community. In 2014, the development of MerlinEM began with Dr. Damien McGralther at the University of Glasgow, supported by our very own Matúš. The first commercial detector was installed in 2016 at the University of Antwerp within the electron microscopy for the material science facility. We quickly started engaging with the electron microscopy community and joined the ESTEAM project. This is a collaboration supporting transnational access to state-of-the-art microscopes in Europe and is supported by some of the largest universities in Europe, including the Ernst Rusker Centre in Jülich and the University of Oxford. There have now been over 60 publications supported with Merlin, covering a variety of applications from solar cells to imaging of virus particles. I now pass you over to my colleague Matúš, who will focus on today's topic of 4D STEM with MerlinEM.
Hello everyone, my name is Matúš Krajňák and I'm an application scientist at Quantum Detectors. This webinar will discuss the topic of 4D STEM. Firstly, I will describe scanning transmission electron microscopy and explain why we should want to collect 4D datasets. I'll explain what an ideal detector would look like, and in the following section show you how MerlinEM detector answers these points. In the final part of the talk, I'll show 3 different examples of experiments done with MerlinEM, which have used 4D STEM data to answer questions otherwise not easily possible. So in the first section, I'll describe how improving the detection systems in STEM lets researchers to access more information about the sample and use microscopes to their full potential. Let's start with a brief description of scanning transmission electron microscopy. In the simplified schematic on the left, we see that the beam in scanning transmission electron microscopy is focused into spot, which then rasters the specimen. The beam interacts with the sample and set of detectors is then used to capture the resultant signals. These could be electron scattered to specific areas of space after the transmission, but also analytical X-ray signals. Once the specific signal is visualized with respect to the given probe position, we can recover the image of the sample. The signals can be very wide-ranging. One of the most used techniques in STEM is the detection of electrons scattered elastically to large angles. This is used to recover atomic weight information from the sample. This information is usually captured with annulus-shaped detector with a hole in the center to let the central, more intense part of the beam through. If we capture the center of the signal, we can collect bright field information with large phase contrast contributions. The conventional STEM detectors are generally fast, reaching close to megahertz frequencies. However, these detectors reduce the information-rich signals to a small number of intensities, and the distribution of the electrons is lost in the process. The question is, so can we get more out of STEM experiments, and what can we potentially achieve? To demonstrate this, let's collect the full distribution of electrons once it transmits through the specimen. To do this, we will need to replace the set of annular and bright field detectors with a single pixelated detector. The image on the right, which should now appear, is extracted from Dr. Magnus Nord's paper, shows the beautiful details that are present once we collect a 2D image of the probe for a single position of a scan. So we would be collecting our annular data and bright field data from this. However, we can see there is a lot more contrast. And so, for example, these sets of rings called Lowy zones could be used to find information about the third dimension of the sample. Right, so now let's see what happens when we collect this kind of pattern for each point of a scan. So the first thing we see that collecting a 2D image for each probe position in a 2D scan results in a 4-dimensional dataset. This data, as I shown on previous slide, can be very information rich, but also hungry for the data storage. Comparing with the standard STEM signals, which are usually tens of megabytes maximum size, the 4D STEM can quickly reach tens of gigabytes. To demonstrate how a 4D STEM dataset can be simply visualized, I have created this mosaic of two-dimensional diffraction patterns. The position of each pattern corresponds to the position of the beam on the sample. Once we start zooming this pattern out, we can first see that a faint image starts to be visible, and eventually, when we keep zooming, we can see an image of the whole sample. The image is, however, affected by the pixelation, but once we remove the dark areas from around the disks, which we started with when we zoomed out, we can clean up the image. This is now approximately corresponding to the bright field image of the sample, which was gold polycrystalline film in this case. Collecting the full information about the transmitted beam gives researchers additional advantages. The standard signals can be generated with more sensitivity because we can choose the geometry and the size of the detector after the experiment. This can be beneficial for complex samples where one size of the detector does not fit all, but additionally, we only need to expose the sample once. Therefore, we can preserve it better if different imaging conditions are needed. The wealth of the information offers additional opportunities, which would not be possible without four-dimensional datasets. Techniques like tachography or improvement of imaging of electromagnetic fields will be described in the later part of this talk. I will also focus on the topic of nanobeam diffraction, where a slightly different beam geometry is used to generate also four-dimensional datasets and advantages this can have. So this example shows how we can generate the conventional STEM signals from 4D STEM dataset. MerlinEM users at Technical University in Darmstadt collected convergent beam datasets of titanium nitride and hafnium oxide interface with a 15 milliradian probe convergence semi-angle. We have then used user-friendly LibreTime software, which supports MerlinEM datasets, to plot standard STEM signals in post-processing. You can see that for example, for the high annular dark field signals, these show brighter part of the sample in the bottom, brighter atomic columns, which correspond to hafnium, which is the heaviest atomic element in this sample. The faint contrast from the titanium, which now suffers with the dynamic range of the screen, is also there, but we don't see it as good. But we could up the contrast on the top part. The annular dark field and annular bright field signals, on this diagonal, show more of the phase contrast information plus potential sample damage around the interface. The bright field contrast, as expected in here, is dominated by phase contrast signals. Important point to make is that once a dataset like this is collected, it can be used for additional methods if the imaging conditions are right. It is also possible to distribute it to students or other researchers to look for additional applications which could be hidden in the depth of the 4D STEM data-rich sets. To help to answer also questions, so what to do to detect the 4D STEM, we will step back a bit and discuss the established detection in STEM, mainly CCD cameras and integrating detectors. Microscopy users have always strived to learn the most about their samples, but technical limitations of past detectors have reduced the information available. Standard STEM detectors are able to collect data with megahertz frequencies. However, the information from the moment to space, as I said, is averaged into a few numbers. For a long time, the only way to access this information were CCD cameras. However, they're strongly hampered by their maximum speed and their efficiency. So I'll talk a little bit about this after, but practical limit of 60 frames a second in a CCD camera is very limiting, and especially if the sample is drifting in the microscope or there are additional problems going on. So in general, the quality of accessible data is reduced by the noise, and CCD cameras and integrating detectors must convert the signal. So electrons are converted to light and back through some multipliers, multiplication and stuff. These steps add noise from additional blooming between pixels, afterglow of scintillators, dark currents, variations in detector gains, also the data readout itself, background radiation, various detector types, various damages, and so on. The ideal detector technology for 4D STEM should avoid as many noise sources as possible. On top of this, the detector needs to have sufficient frame rate to get relevant data with maximum speed. It needs to have high enough resolution to be able to capture the physics. It also needs to do it with enough dynamic range, so your researchers are able to collect single electrons from the less bright areas of the frames, together with very bright area in the center of the 2D diffraction image. The detector also needs to collect data with high efficiency, so we want to detect all possible electrons. It needs to be user-friendly, with means to view the experiments in real time. And last, it should supply the scientists with open data and a way to remote control experiments for maximum practicality. Right, so let's jump to the next section, in which I'll describe the technology behind MerlinEM detector and how it fulfills the point I've just discussed. So MerlinEM detector is based on Medipix-free technology developed at CERN. Medipix-free is a hybrid pixel particle counting chip. The image on the left here shows a schematic of single pixel of this detector. When a particle hits the top semiconductor layer of the detector, it generates a large amount of electron-hole pairs. This layer is then biased, and the holes are directed through the bond to ASIC, which then will process the signal. The transfer charge is processed in a fast electronics, and the schematic of the processing is shown up there. And basically, the signal gets shaped and compared against the user-adjustable threshold. Only when the deposited energy is larger, so it overcomes this threshold value, the electron will be counted. This has many advantages. By applying the threshold, which is above the background electronic and thermal noise levels, we remove these unwanted contributions to the signal. By digitizing the information very early, the readout of the data does not add additional noise to it. The base chip consists of 256 by 256 pixels, and all these have two 12-bit counters offering versatile detection options. We can combine the counters to achieve 24-bit imaging, but also we can use them in parallel to achieve zero dead time with MerlinEM detector. Basically, one counter is actively counting the electrons while the other one is being read out. The last but not least point on the slide is that because the detector is covered by this thick semiconductor, in our case silicon layer, we don't risk any damage to the electronics even when imaging central diffraction beam at 300 keV. To demonstrate the possibilities of direct hardware-based electron counting, I have chosen a couple of images from publications by Jamil Mir. The first image shows single electron events captured on otherwise dark frame, demonstrating single electron sensitivity of MerlinEM detector. The second, more colorful one, shows diffraction from a polycrystalline gold specimen utilizing 24-bit counting depth. We can see that the detector was capable to cover the counts from about 2000 on the edge, so which is the profile is shown on the image here, to all the way to the 10 million counts in the very center of the image. Interestingly, the detector is capable to collect these images with exactly the same settings, although, of course, the beam has to be very sparse for the single electron example on the left. The last topic I would like to discuss in this part of the talk is the frame rate of MerlinEM detector. Before this detector was available to us, when I was a student at the University of Glasgow, we were working on proving that a pixelated STEM acquisition will be beneficial for imaging of magnetic samples, especially industry-relevant polycrystalline thin films. I've taken 100 by 100 pixel data using a CCD camera, which took about 10 minutes to acquire. Of course, this was rather slow, but the experiment helped us to develop a methodology with which we can improve signal-to-noise ratio by the factor of 20. Of course, once we have installed MerlinEM detector in Glasgow, the acquisition of such data became much more practical. Not only the same experiment was much faster, but also we could take much larger scans and therefore analyze larger sections of the sample. I'll come back to this a little bit more in the following application section and explain the methodology behind the signal-to-noise improvement. So let's just see one of the points I tried to make about how the quality of the detector, or the ideal detector. It should allow us enough speed and improve what the instruments are capable of. So in the last part of the talk, I'll focus on the applications of the MerlinEM detector in scanning transmission electron microscopy. I'll demonstrate the rapid feedback capabilities of our system as well. The applications of the system are rather wide-ranging, and this is mainly because it offered properties which were not readily available at the time. Apart from the 4D STEM and diffraction applications, which I'll talk about soon, the MerlinEM is also beneficial for EELS and dynamic TM applications, but these are not the topic of today's talk. I've already shown an example of using MerlinEM to generate the conventional STEM data, so I'll take this one off the list. I'll discuss the topic of electromagnetic imaging in further detail, following by a couple of typography applications. I'll then draw similarities between scanning nanobeam diffraction and STEM when using fast pixelated detectors, and demonstrate the capabilities MerlinEM offers in this area. So I mentioned previously that MerlinEM was able to improve the speed of magnetic imaging in STEM. This method, called differential phase contrast, can quantitatively measure electromagnetic fields in the sample. It has a small caveat, and that is that the objective lens of the microscope needs to be most of the time switched off, which affects the resolution. The objective lens would otherwise saturate most of the magnetic samples, and no internal fields would be present to image. The DPC imaging is based on the deflection of the STEM probe when it transmits through the sample. So beam gets focused to a spot, interacts with the electromagnetic field in a sample, and then gets detected after it passes through. So in the detection plane, we are basically looking for the deflection of the disk. I've shown that utilizing a pixelated detector can greatly enhance the signal to noise, but this is not the only advantage. Because we can detect the position of the beam in post-processing with much better sensitivity, we're able to expand the practical resolution of the microscope itself. This was previously limited by the sensitivity of the segmented detector to around 5 nanometers. Utilizing MerlinEM, we were able to achieve better than 1 nanometer size probe. And this is basically the same instrument. It was always capable of doing this experiment, but replacing the detector was the key. In the example on the right, we can still see that the magnetic structure is still faintly visible, even in the more noisy image. But a lot of materials, in a lot of materials, basically we don't see anything. And an example of this is imaging of out of plane magnetized polycrystalline samples. In this case, the situation is even worse because the material is multi-layer, with only a fraction of the thickness consisting of materials with magnetic properties. So in this more complicated formula, it is the cobalt, which was out of plane magnetized. So okay, so let's try to use our standard detection, and basically once we deploy the conventional segmented detector, the signal is totally overcome by the contributions from the diffraction contrast, and this can be simply visualized here. So what we are after is small changes in X and Y positions of this probe. However, when we scan over a sample like this, the intensity inside of the disk redistributes, and this is basically read out as additional deflections and masks the magnetic contrast. But once we utilize a pixelated detector, so MerlinEM detector, we can post-process the data by tracking the edge of the probe, which improves the signal to noise massively. This is shown on the image on the right, where the researchers at the University of Glasgow were able to visualize the domain structure of the specimen and even measure the width of the domain wall here. And just to mention one more time, this is quantitative imaging. So basically we can characterize exact numbers these materials exact numbers of the fields within these materials. Let's now demonstrate the use of MerlinEM software with live imaging. This video will show an example of DPC stem imaging of magnetic material. So let's play it. The sample is a polycrystalline iron aluminium film, which becomes ferromagnetic after it's exposed to the ion beam. In the live analysis view, we can see the dark and bright contrast appearing, which shows the orientation of the in-plane magnetic field within the sample. On the left, we see the live view of the diffraction space. In this case, a view of the central stem disk with the outlines of the detector we used for live imaging. The live view can be used independently of the stem detection for setting system up, for example, to shift the probe to the center of the detector or to define the exact sizes and positions of live analysis detectors. This system was developed to provide rapid feedback for the users, and they need to really know whether the data which is being acquired is suitable for later analysis. In any case, so the differential phase contrast is related to our next application, tachography. The main difference, though, between the two methods is whereas the differential phase contrast measures the gradient of the phase of the sample, the electron tachography used to measure the phase directly. So electron tachography was developed and experimentally demonstrated in the 90s, but until the arrival of fast pixelated detectors, it was limited by the practicality of the experiment. The motivation of electron tachography is to recover the phase of the sample. I'll give a short explanation why the phase, what is phase, and why we would like to detect it. The beam of the specimen can be described by complex functions. They have real and imaginary parts. When the beam interacts with the specimen, its magnitude and phase are altered. Unfortunately, when the beam gets eventually detected, the phase information is not directly available at the detector, and this leads to a loss of important information. For example, very weakly scattering samples with very thin 2D materials or biological specimens mostly interact with the electron beam by altering its phase, so this information is lost. Electron tachography solves this problem by oversampling the imaging and mathematical reconstruction. So instead of collecting data, like we might be used to, frankly speaking, this is undersampled conditions, the probe positions need to overlap like this. Electron tachography even comes with additional advantages. It can be used to correct probe aberrations and enhance the resolution of the imaging. As I mentioned before, biological specimens are weakly scattering, are a good application for tachography, and I'll be showing this on this slide. So researchers at EPSIC, Diamond Light Source, have used tachography with defocus probe to image HIV-like virus particles. This is a significant result because biological imaging is usually done in transmission electron microscopy, so not scanning the beam over the sample. By defocusing the probe, the low dose of 5.7 electrons per angstrom square was achieved, and the sample was not damaged in the process. In this case, MerlinEM detector was used to image 300 kV probe in material science focused microscope with cryogenic holder. To reconstruct the data from the focus probe, iterative tachography methods have been used. Our last application example is also a dose-efficient method. However, in this case, it will be applied in material science. The method is called scan nanobeam diffraction, and it differs slightly for STEM imaging, introduced previously in this talk. Instead of the convergent beam, like we have shown on this schematic, the nanobeam diffraction utilizes small nanometer-sized parallel beam. After the beam is transmitted through the sample, the diffraction pattern in the far field is detected by a pixelated detector. This method is very dose efficient and is capable of collecting information from very, very beam sensitive samples. Once we scan the sample with this probe, 4-dimensional data is again generated. The couple of images on the right demonstrate what a single diffraction pattern in nanobeam diffraction can look like. Images were collected with 300 kV illumination with a small 2 picoamp current. We can see that the sensitivity of the detector needs to be very high. If we plot the data in the linear scale, as shown on the left side here, all we see is a sharp central diffraction beam. To visualize the information actually present in the data, we need to switch to logarithmic scale to see all the spots generated through the diffraction process. And this was done on the right side here. Importantly, no beam blankers need to be used in diffraction due to the radiation hardness of MerlinEM detector. Okay, so let's talk a little bit about the sample which was used in this experiment. So researchers at Cambridge University were studying perovskite solar cell materials, which are very promising technology because they have great solar cell properties, but also they are potentially printable. However, the material contains very small areas of impurities which degrade its properties, and MerlinEM was successfully used to characterize these impurities. The research has been published in Nature a couple of years ago, but the team at Cambridge has since produced a nice selection of publications studying these materials. The MerlinEM detector is crucial in these studies because of its high DQE and ability to rapidly scan the sample. As a last example of the data collected by MerlinEM, we show a study of degradation of the perovskite solar cell material, which is induced by the dose coming from the electron beam itself. The study was relating the dose the sample was exposed in the microscope to the conditions it would have to survive if deployed on satellites in space. The sample was scanned 10 times, and each of the passes exposed the sample to 12 electrons per angstrom squared, giving the overall dose of 120 electrons per angstrom square. Because of the lack of the readout noise in MerlinEM, we can now split acquisitions to multiple passes and see the dynamic development of the sample without additional noise, and hence expand what's possible in electron microscopy. Right, so after this, I would like to sum up. So in summary, I hope that I persuaded you that the collection of 4D STEM data is a novel and versatile option, which helps to answer large variety of research questions. We can now get a magnitude of data more. As I mentioned before, tens of megabytes have now been replaced by tens of gigabytes of research data. This can lead to new techniques targeting specific science which was not accessible before. MerlinEM detector lets scientists to better understand their samples thanks to its low noise, fast framing, high dynamic range, and efficiency. These properties are available due to actual advanced hardware, which MerlinEM is based on, and which this hardware can count electrons very close to the sensor area where the signal has been deposited in the detector. Overall, since our first commercial installation in 2016, MerlinEM has greatly expanded what's possible in transmission electron microscopy and enabled researchers to use the existing instruments to their full potential. One note, which I have not emphasized fully, is that MerlinEM detector uses open data format, and it's possible to remote control and integrate it with various software and hardware setups. A set of third parties have successfully integrated MerlinEM into their software analysis or data analysis solutions, like LibreTem or PyXM open source software packages. Additionally, partners like Nanomegas and CEOS integrated the operation of the detector itself to benefit the fast framing and direct electron detection MerlinEM offers. With this, I would like to acknowledge our customers and partners which helped with data examples for this talk. Additionally, I would like to thank Dr. Damien McGrath, whose vision and prototype work in this area has greatly accelerated research in 4D STEM. With this, I would like to give the word back to Chloe.
Thank you, Matúš, for that fantastic insight into 4D STEM with the MerlinEM detector. But first, I'd like to let all of our attendees know where you can find us next. On the 28th of February 2023, we are hosting a hybrid seminar alongside Nanomegas and TU Darmstadt. The seminar will see Professor Leo Molina Luna's group give a live demonstration of the MerlinEM detector and the Nanomegas Digistar Precession hardware, showcasing 4D STEM and precession. Finally, from all of us at Quantum Detectors, we wish you a very happy holidays.